we've learned about how speed cameras such as this one work. Let's put it all together into one big picture. We started by learning about waves. You were introduced to terms such as wavelength, frequency, period, and amplitude of a wave. You've also seen that the wave speed can be calculated. It's equal to the frequency times the wavelength. We saw some different types of waves. There are longitudinal waves, such as sound waves, where the particles making up the medium oscillate in the direction parallel to the direction the wave travels, and transverse waves, where the particles in the medium oscillate in the direction perpendicular to the direction the wave travels. We considered what happens to a wave as it reaches a boundary. We saw that if a wave is reflected from a boundary with a more dense medium, then it undergoes a phase change, whereas if it is reflected off a less dense medium, there is no phase change. We will be investigating this in greater detail in the next topic, where we'll be considering how spectacles work. We also looked into the Doppler effect. A speed camera uses the Doppler effect to work out how fast a car is going. It measures frequencies very accurately. So the small shift in frequency caused by the movement of the car tells the speed camera exactly how fast the car is going. We looked at relative motion. We saw how we could calculate the relative motion between two objects. We saw that Einstein used relative motion and the assumption that the laws of physics should be the same in any inertial reference frame to formulate the theory of special relativity. We also looked at how an ultrasound scanner works. We saw that an ultrasound scanner uses similar physics to a speed camera, except that it uses high frequency sound waves rather than waves in the electromagnetic spectrum, radio waves used by speed cameras. Your understanding of waves will be extended in the next topic on how spectacles work.